manage organization probabilistic computers.
Yeah, thank you. Can you hear me from the back? Okay, thank you very much. So, hello everyone. I'm Shuvro from University of California, Santa Barbara. I'm a postdoctoral scholar working under the supervision of Kenneth Kansari. So today I'll be talking about pushing the boundary of quantum mechanics and combinatorial optimization with probabilistic computers. So I hope that you will enjoy the talk. So first of all, I would like to express my sincere gratitude to all the collaborators across the globe whose sincere effort and dedicated support kind of like made our project successful. So yeah, let's start the talk. So today I'm talking about periods and P computers. So all of you are familiar with bits, which is the fundamental computing in digital computing. And nowadays, every now and then, we see that quantum computers are making a breaking news. So they are this is a new computing paradigm, and in that quantum computing paradigm, the basic fundamental computational unit is qubit or quantum bit. So like that, okay. So like that, a qubit is the building block of a P computer, a probabilistic computer. So a qubit has a real value input and two value output. And the expected characteristic, input-output characteristics is like this. So if you apply a zero input, this input parameter, then the two states, plus one and minus one, and the qubit will try to stay in these two states equal. Now, if you apply a moderately negative input to this input terminal, then the qubit will spend most of its time in the minus one state, and occasionally it will visit the plus one state. And the opposite will be true if you apply a moderately large positive voltage. Now, this ideal characteristics can be modeled exactly with this equation, but here I want to make the emphasis that we are trying to, we are not trying to use this equation, we are just trying to make the hardware building block for this equation. So hardware is the important thing here. And there are many ways to do this. So we can use magnetic, stochastic magnetic diodes. We can use even digital CMOS and mixed signal CMOS. So there are very ways to do this. And every now and then I also see new device proposals for building qubits. So another takeaway message from this slide is that qubits are a random number generator which fluctuates between states 0 and 1. At this rate of fluctuation can be controlled using external inputs. Okay, so the next question is how to build a P computer out of this multiple qubit units. So obviously you need multiple qubits to solve the full problem. So the question is how do you interact that the qubits interact together and solve the useful problem. So that equation is given by the second equation that is IR equation. And these two equations together describe the operation of the computer. And now, what is the expected behavior of a P computer? So, if you take large enough samples from this P computer, it is expected to follow the Boltzmann law. And Boltzmann law is based on this energy expression, which is at the fourth expression here. And if you look at this carefully, this is exactly the classical energy expression. But here I also want to make the point that this Isaac energy equation is not exactly direct. You can use any type of energy equation you want. And in that case, you have to modify this ISAP interconnect equation accordingly. Now, our dream is to build a P computer which is inspired from physics. So, in physical systems like the gas molecules container, the molecules operate kind of like sparse. They are locally connected and kind of like asynchronous. So we kind of like take the inspiration from physics and we want to build a system that is asynchronous, local, and sparsely connected. And like physics, you have many design choices for building these apps, like crossbar arrays, crossbar arrays, even CMOS, IMC, etc. Now, where are we in terms of this state of the art computers? So this was kind of like show the computer that was used, built using a stochastic number series. It was a 8 computer that was shown a few years ago. And you can see that the discrete bits, the black boxes inside this yellow PCBs. So there are 8 bits there, and they output of the PCBs are connected to the microcontroller, which kind of emulated the synapse. And then output of the microcontroller are fed back to the PCB. That's how the system worked. And it was kind of demonstrated to solve the factorization problem, which is the time problem, which is what you can do soon. But then our dream is to build a chip which has 1 million of such chips in an integrated chip. But then that requires kind of like large monetary input. So in the meantime, we are kind of like understanding the design principles and analyzing something using CMOS-based design using a. And so far, we have been able to demonstrate up to 10,000 PBs on a FPGA. Now, what are the applications of Pico? So over the years, we have found many interesting applications for logistic computers. Of course, for most of us, the combinatorial optimization, where you have to find the ground state of the given problem, or at least you have to give a good approximation to the ground state. And here are some few references from our group and some other groups which use P computers. The other possible application is in the machine learning. So you can use P computers to generate massive data numbers. You can use P computers to train energy-based models and Bayesian networks and belief networks and so on. And there are also some references there, recent works from our group. And the third possible application is in the quantum simulation, where I have spent some time in my life to do these things. So there are two possible ways to do quantum simulations here. So one is the traditional quantum Monte Carlo approach based on circuit order transformation using replicas. And there is a new way of doing this quantum thing using machine learning techniques. So there are also references from our group for these two approaches. So now let's talk about some applications that we have recently worked on. So a couple of years ago, DUA put out a paper in Nature. So in that paper, they use this 3D cubic icing model, spin glass model to adapt it into their quantum mechanics hardware. And they kind of showed that for this size, they compare with 3 analogous annealing algorithms. One is simulated annealing, simulated quantum annealing, and quantum. And they kind of showed that this quantum annealing has the highest of residual energy, which is defined as the energy you get at a given time from the true ground state energy. So the main conclusion was that the quantum annealer has the highest rate of decay in terms of residual energy compared to the classical approach. Okay, so that was kind of interesting because this is the first time quantum computers are trying to beat the launch of the classical optimization. Right? This is the classical optimization problem. The quantum computer was shown to kind of show some advantage. So that kind of was interesting. So we started to look into this problem with discrete time quantum, simulated quantum annealing, because the other SQA that thing that they used was continuous time simulated quantum annealing, and that was a bit algorithmic, so difficult to put into the hardware. But this discrete time SQA is just replicas, physical replicas of things, so it is kind of easy to put into the hardware. And this makes sense because we claim that this can be made very cheap. So you can put a lot of replicas on top of each other. So that was kind of our approach to this problem. And what we and in that case, since we are physically using these replicas, it also makes sense to take the best result out of all the replicas. So, and we use that, and we kind of see that as we increase the number of replicas in the system, the slope starts to go higher. And I'm talking about this absolute. because these are all negative slopes, so I'm just coming on magnitude. So as I increase the number of replicas, the slopes tends to get bigger and bigger. And this was a kind of like monotonic increase across a wide range of replicas that we have seen. So as you increase the replication, it kind of monotonically starts to grow the slope. And at some point around like 2,800 replicas, we crossed the slope that was kind of like shown. Okay, so then one question was kind of like how to explain this increase. Why the slope increases with as I number of replicas. And then we found that we can describe this thing using this extreme value theory, which is widely known in the field of probability theory. So extreme value theory kind of like tells you that if you sample from a distribution which has a mean, mu, and if you take p samples out of it and take the minimum of these p samples, then your expected value of the minimum values would be shifted by the original mean distribution mu by the square root of the amount of samples we have taken, which is in this case p. So it will be like the shift will be proportional to square root of. So that kind of like tells like why this slope will increase. But then there is a little bit of trick here because that theory that I just described requires that p samples need to be independent. It has to be independent experiments. But in our case, when we use discrete time simulated quantum annealing, the replicas are interconnected. So they are not actually independent. But then we realized that we did some correlation experiment and we saw that along the replica direction, the correlation dies off very quickly at a given MCS. So as you increase the number of replicas, you get to have kind of like increasing number of independent blocks. So let's say you are using out 1,000 replicas and your correlation dies at 100. So you kind of like have 10 independent blocks, right? So that's what. So now if you increase the replica to 2,000, then you have 20 effective replicas. So your replica, your slope will go up. So now the other question is like, is this 2,800 replica make sense? And can you put it into a physical hardware? So that was another question, and that's where our collaborators from CMU, Professor Srimani's group, kind of like helped us a lot. So they kind of like took our design and kind of like G displacing and routing. All those different, and they kind of like these red things that were kind of like physically done in the sophisticated software, and they kind of like projected that right around the edge when we need this slope, developed slope, we can do it actually using the modern chip size dimension. So if you want this, so around this 2,800 replicas, it is actually possible to implement a physical chip. So if you do that, then you can see that the original slope of the developed and our slope is almost similar. In fact, a little better, but it wouldn't be feasible there. So the weight takeaway method from this slide is kind of like we can deliver that quantum annular slope using modern chips if you are given the money and before. So that's it. And then we went down. So the previous algorithms were kind of like annealing-based algorithms. So and there are many other algorithms which are not like annealing-based. And one of the state of the art algorithms for solving this type of problem is this parallel. So here we are using an adaptive algorithm where we can do some processing to get the temperature scale beforehand. And we also apply this isoenergetic cluster moves. And then we can compare it on the same replica basis, like isoreplica basis. So we see that although the discrete and simultaneous starts with a higher slope, you can see that the red diamond, but then it starts to plateau at some point. But this adaptive parallel, although it starts a little bit slow, but then at some point it catches up and kind of like goes really sharp, goes down really sharp. And this was very interesting because ICM made a lot of effort. Without ICM moves, we do not see this. So ICM was kind of like very crucial to this part of the thing. And the other important thing is, like we also tried this column for different size of the cube. And it is very interesting because although parallel development is not a paneling based algorithm, it was not supposed to by default give you a collapse. But somehow it does. And that is kind of like still we are trying to understand why it shows the collapse. But since it shows the collapse, it kind of like tells you that this second behavior is a universal. So it kind of like just not a this size thing, it's a kind of a general feature of this algorithm. So this kind of like tells you that if you use the state of the art classical algorithm, you can go beyond what the paneling based algorithms can do and improve the performance significantly. Now, so then we also went beyond and we kind of like try to study the size of this algorithm. So we kind of like do the arbitrary threshold. In this case, we chose the threshold of 0.007. But that doesn't matter. That's arbitrary. But given the threshold, how does your number of Monte Carlo sweeps go in terms of the size? So we kind of like goes like that. And then the other part is like, how does your time to complete one Monte Carlo sweep go? So these two things are important because then you can estimate how much time you will need to solve the problem, to reach that threshold. So if you just to multiply, you need, say 700 MCS to reach the threshold, and let's say each MCS takes 1 millisecond, then you have just need 700 milliseconds to solve the problem. So this is kind of like our estimate. And so we unfortunately we didn't have the size dependent data from the D-Wave. So we are just comparing with CPU and we are providing a projection based on this nanometric computer. The green things are on the FPGA. So that is measured on the FPGA. And based on some realistic experiments on the stochastic that projection was made. So, and if you look at this final plot, you can see that that is the scaling difference between the CPU result and the FPGA or the nanomagnetic computer result, and that difference is on the order of 10, which is like the size. So our P computer also kind of like not only provides a refactor improvement, it also provides a scaling. So this was kind of like one recent example that recent work that we just put out on our website. And we are also talking in the reviewers. So next I will give you another example of quantum simulation. Now this is not a classical optimization problem, this is a quantum simulation. So where we are trying to do some quantum calculation. So this was like another paper 2 years before that. So this is actually in the PhD. So what happened here is that they are kind of like two get faster like this. So the yellow balls are kind of like antiferromagnetic coupling, and these blue balls are ferromagnetic coupling. This lattice is expanded. So then they use this transversal model Hamiltonian, and they kind of like define a complicated topologically protected order parameter and studied its thermal equilibrium value. Like how long can it take? So if you start from its initial condition and then let it relax, then how long does it take to reach the thermal equilibrium value? So they studied that property and then they kind of like plotted this result. So they compared against the optimized cluster algorithm on CPU and their quantum annealing process. And they kind of like said that there is a 3 million coexisting between CPU and quantum annealing process. So that was another interesting observation. So we kind of took this problem and kind of like implemented on our computer and emulated on the FPGA, we use 125 megahertz, and we immediately saw that there is a 100x speedup that you can get from our pre-computing approach. And then we did some slice-based projection, and that kind of like tells us that another 400x speedup is also possible. So originally we started with a 3 million x speedup, and now we are down to almost like just on 1 order of magnitude. So that 1 order of magnitude is kind of it could be the real quantum effect, or maybe we need to improve our design or something. That is still not understood. But otherwise, yeah, we are down to this 1 order of magnitude speed up. And so you can think of that a P computer is a classical version of the quantum computer. So a lot of speed up can be of the deeper analog can be explained that because of this just analog hardware. They have an analog chip. So that's because they are getting this speed up. And if you look at this plots a little bit carefully, then you will see that the curves, the scaling of the curves are a little bit different. So now in the original CPU curve, the curve goes like roughly 1.5 ON n to the power 1.5, whereas graph color P computer goes as ON. And this P quantum computer, we don't have this data very carefully, so it is a little bit less than ON1, so it is a little bit less, but it's comparable. So our probabilistic computer also provides, here also our probabilistic computer provides a scaling advantage compared to CPU-based implementation. And you get all these advantage at room temperature and with much less power consumption than the quantum computer. Now, I will give you an example that we are currently trying. So that is kind of like this learning quantum systems with qubits. So here we are talking about like a 1D qubit chain, periodically boundary conditions. And we are kind of like have this CFI Hamiltonian again, and we are trying to learn its ground state. And so the usual approach is to use this restricted Boltzmann machine, which has kind of like become the state of the art machine learning model to do this thing. But if you look at this is kind of telling you that there are two layers, and between these two layers, you have all two connections. Every node in the visible node goes kind of like to all the hidden nodes. So in the hardware, this is actually a little bit difficult to do. So what we actually did is kind of further restricted this machine learning model. So what we did, we restricted the connection from each visible node to only 5 hidden and vice versa. Each hidden node is also connected to 5 visible nodes only, and that kind of easier to do in the hardware because of the fan out and fan in issues, and that allowed us to kind of like emulate 5,000 qubits with just 10,000 qubits. 5,000 for visible nodes and 5,000 for hidden nodes. And then we try to learn the ground state, and this is the result. And you can see the span speed error is very close to the chemical accuracy threshold, which is 1.6 something. So you can get a very good accuracy with this qubit-based approach with and this other restricted Boltzmann machine. So, yeah. I'm too fast. Okay. So, yeah, so this is my last. So this is kind of like our on the top right. I have this hybrid computing setup that we use. So there is a CPU which controls the Western biases that is or the parameters that we use in the probabilistic computer. And then, yeah, the probabilistic computer samples and send the samples back to the CPU. But then there are various choices to, as I said before, that there are various choices to build this computer. You can use CPUs, you can use GPUs, you can also use FPGA like we did. And the other interesting thing, you can use multiple FPGAs interconnected to increase the number of qubits that you can. And finally, the third choice is totally different type of things like using stochastic nanometers. And each of these design choices has their own benefits and kind of like complexities. So if you use CPU, no complexity is readily available. You can do it today. You can put as many things as you need, but then you get your speed is very limited. Right? And the measure of this speed in this instance is fifth per nanosecond. So how many things you can do in a given nanosecond? So you can see that number is very small for CPU. If you go to GPU, it's a little bit bigger, but it's still not that much. If you go to FPGA, even higher. But then each of the time you are going up in the ladder, your implementation complexity is increasing. Because now, whatever you can do easily with CPU, you have to write custom Verilog codes for that, and so on. And if you go to this monolithic, then you have to kind of resolve the design challenges and build this nanomagnetic things. So, but then the output is very high. So your energy throughput, so sampling throughput and energy efficiency would be very high. But then there are some design challenges. They are not readily available here. You have to kind of do all these things. And here is a kind of like comparison where we try to compare with GPUs, TPUs, and our thing on the same problem. So all the solvers are using the same problem, which is a bipartite graph. Because of this, usually that is what is reported with TPUs and TPUs. But you can see that our page approach is much more energy efficient than the corresponding other choices. And our projection is that if you use a nanomagnetic probabilistic computer, it will be much more energy efficient, as you can see from the this plot, and it will give you that you have a large sampling throughput with very less power consumption. And the projection that I said that you can have this 1 nanosecond stochastic nanomagnetic qubits that has already been shown by various groups. And if you are use this 1 million of your power is just around 20 watts or so. So we have a lot to gain using going to this nanomagnet based qubits by getting a very high sampling throughput and very less power. So that's, thank you very much.
So we have questions. We take these 5 to 10 minutes and see you in the short
Thank you for your talk. It's fascinating, and I don't know much about this, so part of the very naive question, but how is this so energy efficient? What's the underlying principle why there are trade-offs?
Yes. So I can, yeah. So I can tell you that the energy efficiency comes from kind of like these two things. Like mainly because of this. Because if you implement a period using the traditional CMOS, and let's take a linear accuracy of 90 because you have a random number generator. And if you want to design this random number generator using a traditional CMOS based device, you need that many transistors. Right? If you use a good quality number using a Shuvro based random number, you need kind of 11,000 transistors alone. Just for one period. And that is alone for your arrangement. Random number, and then you have to kind of like design other things also. Right? But then, if you design with assembly circuit qubit, you just have total. Right? So there is a use gate because each transistor will consume some power, right? Static power. So, that is kind of like D1 is kind of like for your less power.
That's amazing.
Thank you, Victor. I'm wondering, the power operating the PV is possible or not? I read some paper, so you are and is it that in the nature of the there assumes asynchronous architecture, and it seems for me that the power operating is okay. But in the nature electronic space, that's describing equation factor implementation. In that case, power operating is prohibited, so that's why you need a parallel grouping of the so what's the difference when we can update the PV in parallel or
No, this is a very good question. So the subtlety is like technically you are not supposed to allow to update bits which are connected to each other at the same simultaneously. Then there is a chance of kind of like case. Or what will happen is that they will get locked if the weights and biases are kind of like heavy, then they will try to get blocked. So even for example, we have these two units, for example, in 0, 0 state, right? And then there is a kind of a strong anti-ferromagnetic bond, let's say between them. So you expect that since there is an anti-ferromagnetic bond, you expect that one is zero, then other is zero. That is the constant, right? One is zero, then other is zero. This one is zero, then this one is zero. But then, since they are updated together, they have not enough information to know which is the other neighbor can do. So they will try to operate at the same time. So if you start from 0, 0, they will both. So these people will see that, oh, this people is 0, I need to make V1. And these people will say, oh, this people is 0, I need to V1 also. So if you update them together, they will both V1. So now it is 0, 0 to 1. And then vice versa. So they are 1, 1. And then this field is saying that, okay, this field is 1. So I need to be 0. And this field is saying that, okay, my neighbor is 1, so I need to be 0. So then they will again field together and they will become 0, 0. So instead of going to 0, 1 or 1, 0, they will kind of come and make it 0, 0 and 1. 0, 0 and 1. So that is the kind of the problem. But then if you if you do asynchronous operation, what we can safely assume sometimes is that there is a very little chance in an asynchronous system that two of the bits will update at the very same time. So if that doesn't have an offset, then you can get there will be some error, but an error in the sense that if you don't update them in parallel, then let's say you need 1000 MCs to solve the problem. But then there is some error then it will probably take 1000 for example. Making, but then it will still solve the problem, but it will be a little bit delayed because of this error. Because some periods will be kind of like time to solve and then kind of like go to the longest and then come back to the lightest something. Yeah.
So I'm kind of thinking thermodynamically. So these converge very nicely. Is there any kind of theorem that says it always has to converge? Because like I could imagine there could be some kind of oscillating mode that gets set up, or is there something like an entropy you could define where like it always has to increase its randomness until it reaches steady state? Like, do you know it's going to reach steady state, or is it just that's what you always find?
A lot of echoes. How do I?
Yeah, so it sort of is an analog of thermodynamics, right? Where it reaches like a equilibrium distribution. But like, is it provable that it will in this particular system, or is it just like what you always find? Like, is there something like an H theorem that says that, you know, eventually will maximize its entropy? Is there something like a generalized entropy?
No.
So,
having the given system, given initial state, and let it go, then it will always try to minimize this energy and kind of like go to the normal equilibrium.
but do you know that? Like, is that proven, or is that just like what you find?
Then there is nothing.
If I can comment on that, so it's proven because the system is a Markov chain model. So we have an update kernel, and the update kernel will be the signal that we're calculating, and basically you can prove by putting meter balance, and it's proven for pivots that it needs to converge the Boltzmann distribution for sure. That's if you take a fixed beta.
And you have to take like long enough samples.
Yeah. So
If
basically,
you have to take it literally takes you to go to the equilibrium.
Yeah.
Then it will solve the Boltzmann.
But how does it agree with your statement that you take the best replica?
Oh, but in that case, I have to use analytic. I'm not because I'm not equilibrium. I'm doing that. So if you will go eventually go to log, you go to log in into a particular of this. You don't have to do the normal equilibrium. You just go to log with one thing.
But when you use replica, you simply generate replicas and then you choose the best one or going to be generated, so it's not getting to any equilibrium.
in that situation,
Yeah.
focus would be to find the ground state. So at that point, you don't care about sampling for the Boltzmann distribution for the sake of getting an even representation in the entire state space. Because that usually is also something you can only do when the space is small enough that you can realistically sample to the end states. But in that situation, you only want to get to the solution. So at that point, you use only every trick possible to get to the solution faster.
I have a question about, I think you showed why don't you correctly two different plotting approaches, if not, was it the one toward the end is an optimizing system architecture, right? But then one you showed was like differently, the calcium for the magnitude, the boring grade, and that, what was the setup? What was the, how were you able to simulate like that transmissible? Is it not only
Just to do a transformation. Right, so if you just to do a transformation, let's say you have one in chain of qubits. What is that? So these are qubits. But then you can substitute of the product transformation and then there's that it is because this one chain of qubits which transfer things. But then since
you need some extra.
yeah, exactly. And then they are
So you're actually setting up a path and then kind of running the dynamics you have to that one.
So the idea is kind of like the big structure. So I can literally put this down.
Yeah.
If these are not kind of achieved, then that will just.
It's literally the question is, does that only work for some kind of quantum dynamics?
They definitely.
It has to have a certain kind of.
Right.
Nice snap in the classical.
Exactly. If these are classical and robust things, so it kind of like not expected to solve the, I mean, as a replacement of qubits. Right? It doesn't have the superposition property or the entire boundary property. So a certain class of problems that people get solved.
Like special class.
Right, special.
Okay, that's really interesting. Okay, I think that's almost all the time we have, so unless there's a compressed 30-second question. Thank you, Brogan. Yeah.